All right, so my name is Tamer. Today I'll basically build on Aaron's slides. So I'm gonna show you some interesting use cases of induction and type level programming in general. So first, let me put you in the context of the slides. So I'm working on a side project called Troy. It's basically a driver for Cassandra. And first, let me show you a demo. So the idea of Troy is basically you provide your schema inside your code base, like create table statement. Then you write your queries. The compiler should validate those queries against the schema above. So in this example, let's do something wrong. Let's change this column name to camel case. So the compiler hopefully should tell you, hey, column reviewer name doesn't exist in table posts. So let's fix that. Fingers crossed. Yep, it works. So as you could see from here, this is using a macro from the annotation or from the logging. You can tell me, hey, this macro, you can do whatever you want. This is not really any induction. So I will switch to this other example, which is not using macros, but this is basically what the macro spits out. So your schema is basically a bunch of facts. Those facts are written as implicit values of some type classes. Your queries are like you call a function called select. This select expects some implicit parameters and some magic that I'm gonna explain. But let's do the exact same example. Let's change this to reviewer name and wait for the compiler to fail. And here's the error message: column reviewer name does not exist in table posts. And to fix that, let's go here and make this camel case as well. And it works. Now, back to slides. Hopefully I caught your attention. All right, so let's actually build Troy. Let's build this thing together step by step. So let's start first by something very simple. So we want to write a codec. When you write like select statement or something, you get back from the database bunch of bytes. You want to convert these bytes to Scala types like int, string, whatever. So let's start by a very naive example, probably inspired by the Cassandra Java driver. So we have a codec class. It has type parameter, the JVM type. This should be like string, int, whatever. And the database type, this can be ASCII, varchar, or whatever types that Cassandra knows. Then the implementation is abstract. Then we'll have multiple classes that extend this abstract class for like ASCII. We're gonna provide the implementation. Then we need some way to register those codecs to be able to fetch them when we want. So the implementation that the Java driver does is basically runtime based. So we're gonna register them like some in-memory hash map or something. We're gonna register those instances of codec somewhere in your main function maybe. Then when you execute a query and you want, oh, hey, I want to decode now this column, which is an ASCII, then we write the last line that gets us back that correct instance, which does the job for us. The problem with this here, first, we're doing this lookup at runtime, so we're paying a cost that we don't need to. The other thing, the problem is like the third box, the register codec. If we forgot this line, if somebody removed it, the compiler will not know about it. The code will still compile, but you will get the problem at runtime, maybe after you execute the query, which is even more horrible. So let's fix that. First thing, we need the compiler to be aware about things. If you want the compiler to be aware about something, you probably need to define it as a type. So this ASCII string is not very good for the compiler, so we're gonna write it instead as traits. So yeah, the compiler understand types. So we're gonna write varchar, integer, and so on, the rest of the types we have in Cassandra. Then we're gonna change the Codec class a little bit. So we're gonna remove the DB type from being just a value parameter to be part of the type parameters. Then we're gonna define instances, or let's say things that implementation of this codecs. This codec now basically is a type class, but it has two type parameters instead of one as you're used to. Let's define the instances for this type class. So I'm gonna first say okay, to convert from Cassandra varchar to Scala string, here's the implementation, implicit value, and another one for integer to int. So these implicit is special markers for Scala or for the compiler to know, to be able later to look for them. So now we have basically done the register part of the previous slide. Now we need the part when we look for the correct codec. So to be able to do that easily, we're gonna define a helper function called Decode, accept two type parameters, one for the database type, one for the Scala type. Then we're gonna ask for an implicit instance for the codec for those two specified types. If you found this codec, then please call Decode inside it and give me back the correct value from it. So let's test this code. So we're gonna send it, okay, varchar and string, do you have this instance? So the Scala compiler will say, let me see. So it will search in specific places in the code base. Do we have an instance for codec that's defined for those two types? Yes, we know, it's in previous slide. Yeah, returns foobar, integer and int works. But if you wrote something, a wrong combination, integer and string, gonna fail and tell you, hey, there is no such instance, it's not written. So yeah, you can't do that. Right, so this is cool, but I would like to improve on it a little bit. So my first problem here, specifying two types like varchar and string is a little bit verbose. We can work out one of them. So you can't work out the database type. So if you just say string, this can be in Cassandra varchar, it could be ASCII, can be different things. So it's safer to specify the varchar like that. Then somehow magically the compiler should be able to tell you back, oh, I know, the varchar are strings and here is your value. So let's see how to write that. So we're gonna implement another type class, call it binding. So this bindings accept, so it's a little bit similar to codec type class, but we have moved the Scala type from being type parameter to a type member. And the rule about that, when to put it on a type parameter or type member, think of a type class as a function. So the input of this function, what you want the user or the developer to write to tell the compiler, should be on the parameter list. So the developer here needs to provide the DB type. This is the parameter list. Whatever in the body, this is what the compiler figures out and tell you back. So I want the compiler to figure out the Scala type. This is in the body. I want the compiler to figure out the codec. That's the body. All right? Now, let's implement it together. So the implementation of this binding, I'll first I'll not redefine Codec again, so I'll depend on it. So I'll say, hey, Scala compiler, please look for me for an instance of Codec for varchar and string. If you found it, and I know it's there, here you go. Here's the instance of binding, and the input is like the type parameter is varchar, and the value, the Scala type is string, and the codec is the same codec as you found. We're gonna do the same for integers and the rest of types. Then let's use that. We're gonna redefine our decode function. So instead of using codec directly, we're gonna use binding. So now this decode accepts only one type parameter. So our developer is gonna write one thing, the database type, then give us the byte buffer, then this compiler job to find the correct binding for us. Let's call it. So calling it with a varchar gives you back foobar as a string. Calling it with an integer, db.integer, gives you back an int. This looks a little bit like magic. Like this decode function, like, oh, one time trains string, another time trains int. And like I, as a developer now, if I wanted to write the return type of decode explicitly, would it be string? Would it be int? Would it be D? No, it's not D. I don't know what to write. So the answer for that, the return type depends on something. It depends on the input, on binding. So it's whatever Scala type inside this binding. There is actually syntax to write that. So just say b.scala type. So this is called path dependent type. Yeah, so that's it for binding. Now let's switch a little bit from type classes. Gonna talk about something else, then go back to type classes shortly. So literal types. So if you type in the compiler just a string word, before I've mentioned in the slides that the compiler doesn't really look into strings, like doesn't look into values. But this wasn't like 100% correct. So the compiler can differentiate between literal values you write on your code. And now there is a PR open in Scala, and it's already merged in type level Scala, that allows you to specify this more easily. So we can rewrite greet function to accept only the string word by writing a type that looks exactly the same as the value, but it's different, it's type, not a value, just word between two quotations. So again, the one above is a type, the one below is a value. If we call this greet function with any other string other than word, you're gonna get compiler error. This means the compiler can look into strings and can differentiate between them. That's interesting. Is anybody thinking of what I'm thinking right now? What we could use this for? I could use it to specify column names, table names, anything I want in my schema, any arbitrary string. So this PostTitle here is a type, it's not a value. So I could build some sort of registry. I can educate my compiler about my schema. So I can tell the compiler, hey, this is bytes. All I know, it's a column called PostTitle. You figure it out. Yes, this is possible, and let's build it together. So first, let's do the schema bit. So we're gonna define a type class that basically serves as like facts about our schema. So column has type. The input for this type class is column name, which should be a literal string. The value is any DB type. And the instances of this type class is basically our representation for the schema. So schema fact 1, column post ID has type integer. Schema fact 2, post title has type db.varchar, and so on. Now, we have taught the compiler to go from column names to db type. We have already wrote a type class called binding that allows the compiler to go from db type to the codec. We could simply wrap these up, define another type class that composes these together and goes from column name to codec directly. And the way you compose type classes, basically you define the wrapper type class, the input is column name, the output is everything in the middle, db type, Scala type, and the codec. And the implementation, so we're gonna first ask the compiler, please find the column type for n, so n for column name. Then please find the binding for whatever db type you found in this column type. Then the implementation is going to be straightforward. The db type is whatever db type inside column has name. The Scala type is whatever we found inside binding. And the codec is already inside binding. This is cool, but this is a very teeny tiny problem that this doesn't work. The reason it doesn't work, probably have mentioned before a couple of times in different talks in this conference. Just a limitation in the Scala compiler right now that you can't refer to column has type. You can't refer to it inside the same parameter list. Luckily, there is a workaround that has been used by developers like for years now. So the workaround is basically you introduce another type parameter to basically as an alias or something that refers to the db type. Then we're gonna convince the compiler that that this d should be the db type inside column has name. So this is called type projection. So now the compiler is not gonna only search for any column has name type, but also gonna look into the body that the db type should be the same as d. Now, since we have a name for this db type, we can use it here in binding. So yeah, this is now legal Scala and this works. Using it, just simple, gonna redefine our decode function. Just decode PostTitle, yep, is a string. Decode PostID, yep, is an integer. But by reaching this point, I could claim now my compiler knows about my schema. Any more slides, I'm just like making it even more better to use. Selecting multiple columns. You probably don't want like select just one thing. You probably like want like you have a row like multiple columns and you want to decode them all together. So we want the user or the developer to write any arbitrary number of column names. Unfortunately, you can't do like this 3 dots or like any arbitrary number of type parameters. You could do with values like 3 dots in Java or asterisk in Scala, but you can do this with type parameters. Luckily, we have something else for that. So from ShapeList, we have something called HatchList. So basically, if you compose an HatchList with a couple of values that has different types, it retains the type of every member in this list. So we know here that the first element is int, the second is string, and third is boolean. Nice. I don't really care about the right-hand side of the values. I only care about the left-hand side. I now have something that's basically a list of types. I have integer, then string, then boolean. This is all what I care about. So I could use that to write the selection part of the select statement. So post ID, post title, and whatever columns I want in any specific order I want. So let's build this together. So we're gonna write a type class. The type class's input is HatchList of column names. The HatchList should contain literal types. Unfortunately, this is something annoying with working with HatchList. So I can't say like it's HatchList of something. I know it has to be HatchList of string. No, you just write HatchList and that's it. You have to like rely on good commands or something to make it visible for you as a developer. But yeah, just ignore this fact. The output is an HatchList of Scala type, int, string, and so on. This should be like the function that takes the bytes and give us back the values, the HatchList of the values. The implementation here, so it's gonna be a little bit of induction, as Aaron has explained before me. I will say it very quickly. So basically, when you work with a list, you typically do some sort of recursion. You do something on the head, then you do something on the tail, then you concatenate the result together. Then luckily there should be some base case to terminate this recursion. So we're gonna do the same. So first we need a base case. So the base case here, the HList is empty, like select nothing. That's simple. The output is also an empty list, and we have nothing to decode. Give you back an empty list. Otherwise, if there is at least one element on the HList, I would like to split the HList to head and tail. But we really don't split things on the type level. It's a little bit hard. So the way we do it is the other way around. I would define the smaller bits. I would say there is a head, and there is a tail. The tail should be in HList. Then say, oh, now I have a row decoder of head const tail. So I don't do that. I do it the other way around. Define the smaller bits first. So let's do first something on the head. So I want the compiler, please provide me the decoder for this head, whatever it was. Just look it up. And the recursive bit, just find a row decoder for the tail, for the rest of the HList. Now the implementation. Now here's the concatenation part. Now we can concatenate the results from the head and the tail. So the out is gonna be whatever out inside the head decoder, const whatever out inside the tail decoder, and the implementation of decode is also similar. Let's use this type class now. So we're gonna update our decode function. The input is S for selection, the HList. Then we're gonna ask for implicit decoder, post ID, post title. Then you get them the correct order, of course. So HList of int, string, 42, and foo bar. So this was the first step in the talk. So the rest of the talk will not be educational. It will be more like just showing the solutions, the final state of them now after iterating on my driver. So schema represented as just facts, implicit instances of about 3 or 4 different type classes that represent things in my database, like this table exists, this column has type X, or whatever you want. Queries. So to be able to define like a complex select statement, I had to build something like ADT, but instead of being values, instead of like being case classes and traits, this is all types, no values. So select statement here is a sealed trait of just 4 type parameters, selection and from, where, and so on. Selection, for example, it could be either asterisk or list of columns, like X, Y, Z, and so on. Relations, like if you say like where X equal question mark, this is represented here. So yeah, X is gonna be the column name. Operator, the operator either equals, contains, and so on. So I have like a big family of traits to represent any SQL statement. So the representation of a simple select statement would be something like that. The selection part is literal types, table literal type, relation all types, everything is a type. Now there is a small problem here, or small complication. So if you have your ADT as bunch of case classes or bunch of values, it's so easy to get the table name out of the case class. You can just say like statement dot table, just to get the table name. But with types, it's really a little bit harder. So I can't really get something out of the select trait. I can't get hold of the table name. What's the table name? So to we actually do that, the operation has to be a type class as well. So I had to define multiple type classes, like for example, get table. This basically, the input should be select statement, and the output should be the table name. And the implementation just implicit instance of this type class. So as we have said before in the HatchList induction example, so instead of breaking things down, we define the smaller parts. So we're gonna define, oh, there is selection, there is a table, there is relations. So for whatever those types are, those type parameters, then our instance is basically select statement of S, the selection, the table, the relations, and the output is the table. If I did it the other way around, if I defined like a type parameter that should be S for selection, for select statement, I would have no way to like dig into this structure and say, oh, the table is T. Am I speaking too fast? Yes? No? No response? People sleeping? Cool. All right. Another example. So the bind markers, those little question marks. We want our driver to know what's the type of this question mark is. It's simple with equals, so the right-hand side should be the same type as the left-hand side, simple. But there's other operators like contains, for example. So contains would work with map and list. I'm talking here about Cassandra, so it has like different types than traditional SQL. So contains would work if the left-hand side is a map or list, and the right-hand side would depend. So if this is a list of T, then question mark is gonna be T. If Y is a map of like K and V, then the question mark is gonna be V. And you can have like a table of all the operators, equal, contains, contains key, and in, and so on. We're gonna implement just one example. So contains with list of T. So we're gonna define our type class that basically understands what's the meaning, what's the type of this question mark. So the input for this type class is the table name and the relation. And reminder, the relation was like a trait that has two members, column name and the operation. The output of this type class is should be db type. Let's define implicit instance for this operator. So type parameters, I'm gonna again define it composed rather than defining the whole thing on one go. So we're gonna say there is a table T, whatever, column C, whatever, and element T, the thing that's inside the list of whatever. Given those three type parameters, I'm gonna first ask the compiler if there is column type instance defined for this table, inside this table for this given column name, and the type has to be list of this ET, then the implementation, also has the relation in the next line. The implementation has to be, the relation has to be of the same C and has to be contains as well. If all these conditions are true, then this is your instance you are looking for, and the output of this type class is ET. So basically for every cell in this table, there should be a definition, an implicit def. Now, something more interesting. So this is basically a hack, but let me first explain the problem, then explain the hack. So I did show you in the demo in the beginning, if the column doesn't exist, it tells you explicitly this column does not exist. So implementing this was not simple. So I have a very deep tree of type classes that depends on each other. This, like, let's take the row decoder example. It depends on multiple. So row decoder would be in HatchList. So we'll do the induction. So it'd be like multiple columns, and every column decoder depends on the column has type, the fact. So if we selected column called blah, this specific instance, the one with the red cross, does not exist. But the compiler would not tell you this specific one does not exist. It will tell you the whole thing does not exist. It will not tell you all the details. Just once it hits the first one that does not exist, will just no, there's no decoder for that, and forgets all the details. So I can't really customize the error messages. So the solution I made for that, this is a hack. Don't throw tomatoes at me. So I'll redefine my colon has type. So instead of the output being a very optimistic type, I would write it as either of something on the left should be like error message encoded as an HatchList. I'll show you later how. On the right hand side, this should be the DB type you're looking for, right? Now, when you write your the fact, the instance of this type class, we're gonna use write of integer instead of integer directly. Cool? Now the bit when you want to hold your tomatoes, hide. So there is the low priority type class in the companion object. Low priority instance in the companion of the type class, and the output type is a left of error message, all types, all literal types, and instead of concatenation, this is an HatchList. Yay or nay? Yay! Yay! Cool. No tomatoes. That's a good thing. I was worried. All right. Now let's go a little bit up in the tree. So the type classes that depends on this type class. So for example, bind marker type resolver. It needs to know what's the type of the column to be able to tell you the type of the question mark. So again, we're gonna change the output to be an either of something. Then the implementation is we're gonna have two versions, one happy path and one the non-happy path. The happy path is gonna look for column has type, and specifically it has to be right of list of something. This is the happy path. If this is good, then the output type is right of ET. The unhappy path, if you found the left of error message, then the output is also a left, and either propagate the error message, change the error message, I don't care, right? Just you have to propagate it. Now all the type classes up the hierarchy gonna have to do the same. Do the happy path and the non-happy path. Finally, towards the top of the hierarchy, we're gonna have a special type class that gets the right out of either or fail. So get or else fail, the input is either, the output is the right of the either. Right? So if it's right, then yep, the output is T, no problem. If it's left, then this is a small macro just that concatenates this HatchList and produces the error. Not very good. I'm not very proud about it. I really wanted to do it using implicit not found, but yeah, I really struggled with concatenating the HatchList. So maybe if you know how to do it, please talk with me after the talk. What's more we got? Yeah, so a little bit of sugaring on top of that. So I don't really want my users to write those ugly square brackets. Like nobody's gonna use Troy. It's good for talking, but not really for real life. So luckily, the developer don't need to do any of that. So Scala meta on the top, just sugaring. you're gonna write your SQL as you used, and there is inside the macro, this is a very stupid parser that just takes this SQL, parse it, and just spits out the code that you should have written. So in the top, it just produces a bunch of implicit values, and in the bottom, kind of produce the ADT, the type level ADT I've shown you before. Small problem here, the box in the bottom, the compiler or the IDE doesn't really know what's the type signature of Q before executing the macro, which really annoys IDEs. But luckily, I have a solution for that. So I'm gonna ask the developer or the user to define the case class that represents the row, case class that represents the input. Give me those type parameters. The macro can promise you a function that, given the class input search, is gonna give you like a future of sequence of result. Then inside the code that the macro gonna spit it out is gonna convert from HatchList to this case class using shapeless generic. So if you defined your case class wrong, that doesn't match what you selected, you're still gonna get compile time error. So don't worry. Maybe the only problem, maybe the IDE won't show you like a red squiggles or something, but still, once you compile your code, it's gonna fail. Yep. Finally, the code is all open source. So under the GitHub organization Schema safe, there is Troy and Toy Troy. So Toy Troy is very simple example that I'm using in the code because Cassandra has a little bit different types and complicated rules that I don't want to pollute the idea itself. So use Toy Troy as a proof of concept. Oh, actually, I've renamed it to POC, proof of concept. Sorry, I forgot to change the slides. Yeah, it's now /POC. Sorry about that. GitHub should redirect anyway. And there's /Troy. This is my driver. It's now not in a good shape. So I used to have an old implementation that's pure macros, no type level induction. I'm now moving to the new code base. So a new implementation. If you want to help, yes, please. Yeah. Resources. So the talk that really inspired me was Roll Your Own Shapeless Talk, Scala Days 2016, and the book that taught me the mechanics of shapeless and how to write all of that. Shapeless guide. Just Google shapeless guide. The type astronaut's guide to shapeless. Finally, there's a series of blog posts that I'm lazily writing. So I only write one part before every conference because I have to blog about something. Oh, come, I'm talking in there. So yeah, hopefully I'll write the third part soon, and get in touch with me on Twitter, GitHub, or my website. Yeah, that's it. Any questions? Yes, please. Yeah, so the question is asking about the compile time of Troy. So unfortunately, it's not very good. So on type level Scala 2.11, it takes roughly 1 second to compile one query. I know there's improvements in Scala 2.12 by Miles. I didn't use it. I don't have numbers. It should be better, but I don't have any numbers right now. Thank you. Yeah? So I didn't really get the question. So you're asking, I'm using literal types. This should not compile on lightband Scala, right? So yeah, yes, I'm using type level Scala, but this is only to make the slides pretty. You can still use it with shapeless. I guess I have slide of expected similar question. So you can use like shapeless witness like that. Oops. Oh, it won't show because it's hidden anyway. So just zoom in. Yeah, so this works on normal Scala. I can just say witness dot one between air quotes. This should works. Plus the PR should be merged. I'm not sure when, but yeah, the PR is there for Lightbend Scala. So this should be normal Scala soon. Did I answer all your question? Welcome. Aaron?
Yeah, you originally had it working with a macro. What made you want to switch from the macro to this new representation?
Just because I could. So I will tell you maybe something. So,
Repeat the question.
all right, okay, sorry. So the question is why I migrated Troy from depending on one big fat macro to use type level induction. So I'll tell you there's two things. So first, writing the schema validation by hand inside the macro was a bit tedious. I felt like I'm reinventing the wheel. I'm defining my own type system. I even felt like, oh, maybe I could just open embedded Cassandra or use something from Cassandra. Why I'm doing that? Then at the same time, I was reading about shapeless, like, whoa, that's really cool things. I have to use it. Then I decided to switch Troy. Yeah, thank you. More questions? Yeah, I guess we finished early, but yeah. Okay, guys. Yeah.